Today we'll be looking at week 8 summary. Okay, so this class is basically for week 8 summary, and tomorrow mostly we'll be having tomorrow or the next class we'll be having solve with us, and then we'll see programming questions. Okay, yeah. So can we start? Can we start, or we will wait for 2 minutes? We'll wait for 2 minutes. Okay. Okay. We'll start. Right. So week 8 is about generative models. Right. So week 8 is about generative models. Okay. So before starting, the assumption for this week is like this. Okay. Now we have training data and test data, right? So you want, I mean, uh, for for doing for developing a reasonable model, there should be some relationship between the training data and test data, right? So if you have a training data and your test data is not at all related to your training data, then whatever model you are going to come up with, it's not going to do well in your test data, right? And let's say you have another case where your test data points are just the same as your training data points. Maybe there are some samples of the training data points. Then there's no point in learning, right? Because ultimately you want the model to be useful in predicting the points which you don't know, the data points, the labels for the data points which you don't, right? So both the cases are not okay, right? So our assumption is there is some relationship between the training and test data points, and this relationship is given by a distribution, right? Okay, it's given by a distribution. So if you have to put it in another way, we can say that there is some probabilistic mechanism which generates the features and labels. Okay, so there is some probabilistic mechanism which generates the features and labels. All right. So every pair xi and yi, now every pair xi and yi, there's a data point and there's a label. Okay. Now this every pair is assumed to be drawn from a distribution. Okay. There is some distribution D. Now you don't know what the distribution is, but the assumption which you are making is every pair is assumed to be drawn from that distribution. You don't know that distribution, but the assumption is this. Okay. So this is the assumption with which we will go. Okay. Clear? All right. So this is the assumption. So if this is the assumption, there are two ways we can model. One is the generative model, and the other one is the discriminative model. Discriminative model. Okay. So in generative model, what you're going to model is p of x comma y. Okay. And in discriminative model, you'll be modeling p of y given x. Okay. So here, if you have to read this, if you have to understand this, this is just like saying it is a model which will say the probability of a data point and a label occurring as a pair. Now, as a pair, what is the probability of this data point and this label to be generated? Okay, we have some unknown distribution. Now, what is the probability of this data point and this label being generated? That is being modeled by p of x and y. Okay, x comma y. This is like the joint distribution. Okay. So this is the joint distribution. This is one way to model. All right. Now, maybe see, you want this to be as a pair. As a pair, what is the probability? Okay. Not just as an individual data point, but as a pair, what is the probability? Okay. So that is your generated model. Okay. And the discriminative model is given that some data point has been generated, or you have seen some data point, what is the probability of that label being 0 or of that label being 1? So that is being modeled here. So given you're given some data point, what the discriminative models is the probability of that label being something. There is some data point, you're discriminating it, whether you're saying whether the data point belongs to label 0 or label 1. Okay. And a model for that probability is given by this discriminative model. Okay. So these are two ways to model. And the example for first model is something which we'll see today, which is the naive Bayes and the Gaussian Bayes. Okay. The example is naive Bayes and Gaussian naive Bayes, which we'll see today. And the example for discriminative model is something which you have seen. There can be others, but as of now, we can take this. Okay. So KNN and decision trees. Okay. So in your discriminative model, if you look at this, now probability of y, what is the probability that label is 1 given x is 1? Now this probability will be equal to 1. When will this be equal to 1 in k and in k nearest neighborhood? What is the probability that the label is 1 given x is 1? Now this will be equal to 1 if the leaf node for this data point is 1, right? Sorry, I think I did it. So for KNN, fine, maybe we can, yeah, maybe we can go like this. Now the probability, I'm repeating it again. So what is the probability that the label is 1 for a given data point? That is something which you are modeling using discriminative model. Okay, now if this is equal to 1, what does it mean? Decision trees. If this is equal to 1, then it means that the leaf node is 1, right? You have some data point, it will traverse from the top to the leaf node. And if that turns out to be 1, then the probability of y being equal to 1, given that this data point has been generated, is 1, right? And if this is 1, if this is equal to 1, then p of y being equal to 0 given x will be equal to 0, right? So this is some kind of discriminative model, right? So you are clearly saying whether it's going to be 1 or 0, right? So that's the thing. And again for KNN, if what is the probability that the label is going to be equal to 0 given that some data point has occurred? And if that is equal to 1, it means when will that be equal to 1? When the majority of the neighbors is, I mean, when the labels for the majority of the data points is 0, right? You have k neighbors, and if the majority for the, I mean, if the majority label is 0, then this probability is going to be 0, right? So this is again saying, clearly saying whether it's 1 or 0, right? So this is discriminative model. Is it clear till now? Fine. Right. So the important thing is, this is modeling the joint distribution of x and y, and this is modeling the probability of y being equal to some class, given that this data point has occurred. Okay. Now here, if you look at this, I mean, if you expand this p of x is x comma y, this will in turn model something about the data point also, right? Here, if you look at this is not modeling anything about the data point. But if you expand this, this can be equal to p of x into p of y given x, or it can also be equal to p of y into p of x given y, right? So in both the cases, it is modeling something about the data points also. Here it's modeling something about the data point. Here also it is modeling something about the data point, but again, given something. Okay, but still it's modeling, right? So this, we will use this generative approach if we can make some reasonably good assumptions about the way the data points are also generated. Okay, so if we can make some good assumptions about the way the data points are generated, then we can follow this model. Okay, but if you are not able to make any reasonable assumptions about the way the data points are generated, then it is good to stick with discriminative model. All right, so that's the key difference. And what we will do in week 8 is we will make some assumptions about the data points also. Okay, we'll make some assumptions about the labels and also the data points. So that assumptions, based on that assumptions, we are going to come up with two algorithms, which is the naive Bayes and Gaussian naive Bayes. All right, fine. So this is the broad introduction. Now, before going to these algorithms, what we will first do is we'll take an example, and the way we'll develop these things is through this example. Okay, so basically we are going to look at an email spam classification problem. Okay, now every data point is an email, and the label is going to say whether it's a spam or not. Okay, every data point is an email, xi is an email, corresponds to an email, and the label says whether this email is a spam or not. Okay, so this is the training data. All right, now if you look at xi, the data points itself, now this data point, every feature is a binary feature. Okay, every feature is a binary feature. That is, you have d features. Now every feature can either be 0 or 1. Okay, now what does that mean? What does that mean? Let's say you have some 1,000 data point, I mean some 1,000 or 10,000 words in your dictionary. Now every word will correspond to one feature. Okay, so every word will correspond to one feature. Let's say feature 1 is apple, feature 2 is ball, feature 3 dot dot dot, and feature z is zebra. Okay, so like this, you have maybe some 10,000 data point, 10,000 words in your dictionary. So for every word you are going to have a feature. Now if some label, if some data point, if that email has the word apple, then it will be 1. If it does not have the word ball, it will be 0. And like this, let's say it has the word zebra, then it will be 1. Okay, so if that corresponding word is present, the label is 1. If that corresponding word is not present, then if the corresponding word is not present, then the label is 0. Okay, so this is the way our data points are set. Okay, all right, so what we have to do is we have to model this, right? We are looking at generative model example, right? So what we have to model is p of x comma y. Right, p of x comma y. Okay, so this is what we are going to model. Now, as I mean, this one I showed you earlier, right? So this can be written in two ways, right? Now p of x comma y can be written as p of y given x into p of x, or it can be written as p of x given y into p of y. Okay, so this comes from the base rule. So like p of a given b. Okay, so this is equal to p of a and b divided by p of b, or it is also equal to p of. Okay, so this is base rule. Now we can take this to the other side. All right, so this can be taken to the other side. So this will mean that p of a and b is equal to p of a given b into p of b, or it is also equal to p of b given a into p of a. All right, so this can be written in two ways. All right, so let's look at the two ways and see in which way we are going to model. All right, now look at the first way. Now p of x comma y, this is the thing which you are going to model. Now this can be written in this way, right? P of y given x into p of x. Now what does this mean? What is p of y given x? This one we have already seen, right? The discriminative model. P of y given x says that, now given that there's an email, now given that some email has been generated, what is the probability that this email is a spam, or what is the probability that this email is not a spam? That is what is being captured by this, right? Right? You have P of y given x, this captures the probability that some email is a spam or some email is not a spam, given that this email has been generated. Okay. Now P of x is nothing but the distribution of x, or the P of the probability of seeing this email. Now we assume that there is some generative mechanism, right? We assume that there is some mechanism or there is some distribution D which generates all the data points, right? Which generates all these pairs. Now in one of these, if there is some email X, what is the probability of that mechanism to generate this email? Okay, so that is given by this. All right. Now these are two things. Now let's look at this and come back to the last one. Now there's another way, right? Now P of x comma y can also be given as P of x given y into P of y. Okay. So P of x given y into P of y. Now what does this mean? What does this mean? So given that, now this means, maybe I can give an example. Now given that what we are trying to model basically is probability that an email is equal to hi, how are you? Okay. Now what we are trying to model here is what this model is probability that an email is probability that email X is equal to this, given that that email is a spam. Okay. Or given that it's not a spam. So given that an email is not a spam, what is the probability that that email is going to be this? Right? Now, if it is not a spam, it can be many things, right? If this is not a spam, it can be either this, or it can be come to the office tomorrow. So it can be anything, right? So given that some email is not a spam, it can be anything. And for each of these emails, we are going to try to model the probability, right? So this is what is being modeled here. All right. And what is P of y? P of y is the distribution of labels, right? You have either the label is either 1 or 0, and what is the this distribution is that probabilistic mechanism which generates these labels, right? So this is what is being modeled here. So till here is everything clear? Is there any doubt? See, there are a few things. P of y given x is some email is given. Now, what's the probability that that email is a spam, or the probability that that email is not a spam? Okay. And P of x is the distribution of the email itself. Okay. And P of x given y is, now given that that email is spam, what is the probability that the email is going to be equal to something? Okay. So that is being modeled here. And our class P of y is the distribution of labels. Okay. So these are the 4 things which are modeling. All right. Now, which one to choose? Which way to go? Okay. So which way to go? Now, if you look at the first one, now ultimately for prediction, we need this, right? Now, the end goal of binary classification is what? To get this one, right? Whether you're going directly or you're going in a different way is the question. Now, if you're able to model P of y given x, then there's no necessity to model P of x, right? You're able to model P of y given x. So given any email, you have a model of the label, then why do you need to know the model of the data points itself? If you can model this and if you can come up with an efficient model, then this is not necessary, right? But if you look at the other side, what you would see is, if you model this one, if you're trying to model it in this way, then what you will get to know is you will be able to estimate the I mean, if you know what is P of Y, if you know the distribution, then you can, on an average, say how many emails are going to be spam and how many emails are not going to be spam, right? If you know this distribution, then you can make an reasonable estimate, right? So this is something which you will gain here. What you will also gain is, now there are two classes, right? There are two classes, which is class 1 and class 0. Now for every email, now for P of x1, we are going to model P of x1 given 1, that is P of x given y, right? P of x given y, which will be P of x1 given 1, P of x2 given y given 1, dot 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 we'll do. And similarly, we'll also model P of x1 given 0 and P of x1, P of x2 given 0. Like this, we are going to model. So like this, for all the n data points, we have the distribution of the mails for both the models we are having, right? So, I mean, for both the classes. For class 1, we have the distribution of emails. And for class 0 also, we have the distribution of emails. Now, this will give some insight again, right? So, you are able to get some insights in this side. Whereas, if you model this one, then there's no necessity to model this one, right? So, now because of this, we are choosing this way, right? Okay. So, because of these two reasons, broadly, we are choosing this model, okay? So, we are going to go this way. That is, we will model the distribution of labels, and we'll also model the probability that some email is going to be equal to something, given that that email is a spam or it's not spam. We are going to model that. Okay. All right. So this is what we are going to do. Clear? So if this is clear, then we can go to generative approach. If that is not, you can ask your doubt. Is there any doubt? There is no doubt, we can go. Fine. Okay. So we are going to go this way. All right. Now in this way, we'll start with a generative story. Okay. Now this generative story for I mean for for understanding purpose, we'll start with d is equal to 3. Then later on we'll generalize it. Okay. So that's what we are going to do now. Now this model is like this. Okay. So first we are going to the label, right? We have to model two things. One is the distribution of the labels itself, and the other one is P of x given y, right? So these are the two things. Now, first one, what we are going to assume is P of y is determined by a coin. Okay, you will toss a coin. Now, if that coin falls, if that coin is going to be head, then the label is going to be 1. If the coin is going to give you a tail, then the label is going to give you 0. Okay, so this is the distribution for y which we are assuming. Okay, so if this is the distribution, then there's going to be some probability, right? So there's going to be a probability with which you're going to get a head, and there's going to be some probability with which you're going to get a tail. The sum of both should be 1. So probability of heads is going to be p, and probability of tails is going to be 1 minus p. Okay. So when you sum both, you're going to get it. Okay. Now this is, what does this mean? The probability of that an email being spam is given by p, and the probability that an email is not spam is given by 1 minus p. Okay. So this is the model, and when you flip the coin, if you get heads, you will go in this way. When you flip the coin, if you're going to get tails, you're going to go in this way. Okay. Now let's say you flip the coin once, you get heads. So you're going to say that the mail is going to be spam. Okay. Now we have 3 features. Okay. We have 3 features. If you have 3 features, then what are the all possible emails? Right? These 3 features corresponds to 3 words, right? Word 1, word 2, word 3. So how many ways can you combine the words? There are 8 ways to combine, right? There are 8 ways to combine. Now every word can be present or not. So every word can be present or not. For the first word, there are two possibilities. Second word, there are two possibilities. And for the third word, there are two possibilities. So 2 into 2 into 2 is going to give you 8. So there are going to be 8 possibilities. Now, what are the possibilities? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are the 8 possibilities, right? Now, for all these 8 possibilities, now if it is a spam, there can be 8 possibilities. Similarly, if it is not a spam, it can be 8 possibilities. Okay. So one thing which you have to notice, just because it's a spam, and if it's not like this 000 can occur only if it's a spam, or if this 000 can occur if it is not a spam. Okay. So any email, any given piece of text, or any given piece of text as an email. Let's say, hi, how are you? Okay. Now let's say now this email can be from your friend, or it can be from some random stranger who's sending mails just like that to anybody, right? So it's possible on both the cases, right? So similarly, all these possibilities are possible on both the cases. Okay. So what we have to do is we have to look at the possibilities and try to estimate the probabilities. Okay. Now, given that it's a spam, given that a mail is spam, what is the probability that that mail is going to be equal to 000? Okay. So this is for this data point. This is for this email. Now, given that the email is a spam, what is the probability that the email is going to be equal to 001? That is given by this. Now, given that the email is a spam, what is the probability that the email is going to be equal to 010? That is another thing. Okay. So like this, you will model for all the 8 possibilities. And here also, given that the email is not a spam, given that the email is not a spam, what is the probability that the email is going to be equal to 000? Okay. And what is the probability that the email is going to be equal to 111, given that it's not a spam? Okay. So like this, we'll model for all these things. All right. So what we are trying to model is probability that X is the email is equal to hi, how are you? Okay. So given that it's a spam, and we are also going to model the same given that it's not a spam. Okay. So these are the two things which we are going to model here. All right. So, but whether it's going to be 1 or 0, that will be decided by the coin flip. Okay. So once you have decided that, you will model this. Okay. So this is the generative model. Now for every data point, you are going to generate what I mean. If you what the assumption is, see the assumption is every data point is going to follow this model. Okay. First you will flip the coin. Then once you flip the coin, an email is going to be generated with this probability. Okay. And an email is going to be generated with this probability, right? So what does that mean? Maybe I can go to Colab. What I'm trying to say is, let's say import number, or let's say import this. Okay. Random dot randint. Let's say, or maybe random dot rand will give some number. Okay. From randint. Okay. Let's say 0 to 10. Okay. So it will randomly generate some number. Okay. Now there is some probability distribution inside this. Okay. There's some probability for 5, there's some probability for 4, and like this it's there. So similarly here also, for every email there is some probability. Now with this probability, some email is going to get generated. Okay. So that is the assumption. With this probability, now there's probability for every email, right? Now with this probability, some email will get generated. Okay. And the coin flip is also like this. Whether you're going to get a head or tail is also depending. It's also from this. Okay, fine. So this is the generative story, but the issue is now if the issue is you have too many parameters to estimate. All right. So if you look at this one here, if you find all these 7 things, you can find the last one, which is 1 minus the sum of all these things. And the same case here. But how many possibilities are there? For 3 features, you have 2 power 3 possibilities. Then for D features, you will have 2 power D possibilities. Right? For D features, you have 2 power D possibilities for this side. And if you 2 power D possibilities, but only for the last possibility, you need not model. Right? You have 2 power D possibilities, but for the last one, you need not model. If you find the other things, you can find the last one. So you have 2 power D minus 1 for one side, and you have 2 power D minus 1 for the other side, which is 2 times 2 power D minus 1. And you also have to find this P, right? You should also find this P. So these are the number of parameters, okay? So these are the number of parameters, the one within the brackets. Now if you evaluate this, this will turn out to be 2 power D plus 1 minus 1, okay? So 2 power D plus 1 minus 2 plus 1, which is minus 1, okay? So you have these many parameters. Now this is exponential, right? So this is definitely not going to be feasible, right? So it's going to be computationally infeasible, okay? So even though this looks like a good story, good generative story, but still, since, I mean, due to computational constraints, we are not going to model this, okay? So is there any doubt? Is it fine?
Sir,
Ah.
regarding this P, which is deciding whether it is going to spam or not spam, right?
Ah.
Here we are assuming that we are flipping a coin, right? But how can we relate to this reality? How this P is decided? How can we say that?
See, see, if you flip a coin, you're going to get it right. If you flip the coin, you're going to get it right. If you flip the coin,
Sir, here we are considering that there is a coin with
ah.
some probability P.
Hmm.
But how to relate in reality that how this is going, this P
No,
is
no,
going to
like
come.
it's, see, that's what these are all assumptions, okay? So these are all assumptions, all right?
Okay.
So
Sir,
it may
then
or may
how
not work.
it is going
Ah.
to help us in real life, sir?
No, no, these are assumptions. You'll try this once. If this works, you'll do it. And you have some, if you have some domain knowledge, you can come up with different models. I mean, if you have domain knowledge, you can come up with different models. Now, for learning purpose, this is one of the models. All right. So you're assuming that there is a generative model. Okay. And that one of the assumptions is this. Okay. You're assuming it may or may not work. Okay. In reality. All right.
Oh, okay, sir.
Yeah. All right. So this is the generative story, and this story is not going to be computationally feasible. So we will not model this. There's no point. Okay. But what we will do is we will model this generative story. Okay. So if you look at this generative story, now the distribution for y is still the same. The probability that the probability of spam is p, the probability of not being a spam is 1 minus p again. Now given that it's a spam, okay, now given that it's a spam, now instead of looking at all possible emails, what we will be looking at is all the features. We are going to look at all the features. So this is feature 1, this is feature 2, this is feature D. And similarly, this is feature 1, this is feature 2, and this is feature D. Okay. Now these are all again coins. Okay. So these are all coins again. All right. Now this is a coin. If the coin turns out to be head, you will get 1. The coin turns out to be tail, you will get 0. And there's a probability, that probability is given by P. Right. So similarly, these are all again coins. Now the probability that feature 1 is going to be equal to 1, given that it's a spam, is given by this P power 1 and subscript 1. P11, if I can call it. So this will be called as P12, P1D. Okay. So the power at the first and then the subscript next. So P11, P12, P1D. Okay. So this is going to be P01, P02. Okay. And P0B. Once again. P01, P02, and P0B. So what this is basically saying is, first you will flip the coin. Now if it turns out to be head, you will come here. Now the way you will generate the email is given by these coins. Okay. The way you will generate the emails is given by this coin. Okay. So let's say, again, apple, ball, cat, dog. Okay. Let's say these are the 4 features. Now how you will generate is, you will flip the first coin. If you get head, then you will have apple in the email. Now you will again flip the second coin. If you get again 1, you will have ball in your email. And you will flip the next coin, and if you get 0, you won't have cat. If you flip the next coin, you get, and again you have 1. Again, if the coin turns out to be head, you'll have dog in your mail. Okay. So this is the way the email is generated, and whether that email is a spam or not is decided by this coin. Okay. So if it is spam, we'll come here. If it is not a spam, we'll come here, and the email will be generated according to these probabilities. Okay. Clear? So this is the generative story here. So this is P of y, the distribution for y, and the distribute. Now this is given. Now what is this? So this is now for a particular mail. For a particular mail, you are going to have D features, right? Now the probability that the ith feature is going to be equal to 1, given that it's a spam, is given by this one, P1I. Okay, and the probability that ith feature is going to be equal to 1, given that it's not a spam, given that the mail is not a spam, is given by this P0I. Okay, so now this one, if you want an example, let's say for a particular feature, the word is lottery. Okay, the word is lottery. Word is lottery. Now if this coin turned out to be head, okay, then it's a spam, right? Then if that is a spam, now given that it's a spam, what is the probability that the email will have lottery? There's going to be a high probability, right? So let's say 0.85. Okay. Now again, for the same one, now with what probability? Let's say y is equal to, this is for y is equal to 1. And for y, if it is given that the email is not a spam, then the probability of that word being the lottery being in that email is going to be less. Maybe it is 0.02 or 0.15. These two need not be the same, but what I'm saying is let's say 0.02. Okay. All right. And the probability that the word is not going to be in the email, given that the mail is a spam, so this will be equal to 1 minus 0.85. Okay. So this will be equal to 1 minus 0.85, that is 0.15. And this will be equal to 0.98. Okay. All right. So if it is given that the email is a spam, then the probability that the lottery is there, the word lottery is there in your email is 0.85. And given it's not a spam, then the probability that the word lottery is there in your email is 0.02. Okay. So this is what is being given by this one. Okay. Now this corresponds to these coins, and this corresponds to these coins. Okay. All right. So this is the generative story. Is there any doubt? The generative story here. Is there any doubt? So for every word you will check. Okay. So if it is a spam, what is the probability that this word will be there in the email? And if it is not a spam, then what is the probability that this word will be there in the email? All right. So this is what you are going to do. All right. So this is the generative story. Now, based on the coin tosses, the email and the label are going to get generated. Okay. The emails and the labels are going to get generated based on these coin tosses. That is the assumption which you are trying to make. Okay. So this is the assumption which we have made. Okay. Now, before proceeding further, we must notice one thing. Okay. We must notice one thing, that is, yeah, I mean, that is there, but one more thing is how many parameters are there. Okay. So here there are D coins, here there are D coins, and here there is one P. So 2D plus 1 is the number of parameters. Okay. So this is fairly straightforward. Okay. All right. So these are the number of parameters. So this is linear, right? So this, it will work. Okay. Even for a large number of words, it's going to work still. Right. Now what we are going to, now this is a good model, right? In terms of computational complexity, this is a good model for us. But this model is missing something. Okay. So what is it missing? That is what we are going to see. So one thing that being missed is, now if you look at this, what we are trying to model is P of X given Y. That is this part. Now what is changing from this one and this one? What is changed from this model and this one? P of X given Y. That is this part alone is changed, right? This one is still the same. Here also this is same, but this part has changed, which is P of X given Y. So that is being changed. Now once that is changed, what you are seeing is P of X given Y is given by P of X is equal to some F1 to Ft, right? So as I told earlier, this will be like, so if you want, what is this? This is the same as apple, comma ball, comma cat, comma dog. Now this, I mean, you will not have just four words. You will have for all the words, but for these words alone, you will have one. For the other places, you are going to have zeros. Okay. So the probability of X being equal to this email, given for some Y, is given by this. Okay. P of X being equal to this email, given Y is given by this quantity. I mean, based on the label, one of these two. Okay. So let's say if the label is 1, then it is given by F1 comma F1, P of F1 given 1 into P of F2 given 1 dot into P of Fi given Fn given Fd given. So okay. So what this means is, I mean, if this is the model which we are assuming, then the assumption being hidden, the hidden assumption being made is the presence or absence of some word has no influence on the presence or absence of some other word. Okay. What I'm trying to say is the presence of the word lottery has no influence on the presence of the word, let's say dollar. Okay. Let's say rupee. Okay. So the presence of word lottery has no influence on the presence of the word rupee. Okay. So this is the assumption which is hiddenly being made. Given that we are making this, if we are making this assumption, then this assumption is also made, right? Because for any 2 coins, the coin toss are independent, right? That is obvious, right? You have 2 different coins, you are tossing them separately. So even if you toss them together, still it won't, I mean, maybe it might matter, but here it looks like we are tossing it differently. So there is no influence of the result of this toss and this toss, right? So that is the hidden assumption being made, but this is not always true in reality, right? So if this is the assumption which is hiddenly being made given this model, this need not work in, I mean, this need not be the way things are actually there in reality, right? So the reason is like, now these are emails, right? These are emails, so they are going to be in some language. Now this language will have some grammar, there are going to be some semantic structure, and if some word is present, some other word will be present. If some word is not present, then the other word will not be present. Those things are there, right? So those things are not captured here. Okay. It does not capture the grammar or the semantic or the context and all those things. It is not being captured here. Okay. So that is the issue of this model. But what Sir has told us, it reasonably works in practice. That's what he has told. I have not tried it out, but that's what he has told. So as of now, we can maybe stick with that. So, but why we are doing this model is, yeah,
Like in practice, how does it differ?
that's what. So in practice, this may or may not work. Okay, this may or may not work. So because like maybe, I mean, maybe there is no connection sometimes. Most probably there will be some connection. But this 1 0 need not always be about emails. Maybe it is about something else also. In our case, we are looking at emails, but maybe there are some other, there can be some other examples also, right? I mean, I have not tried this model many times. Okay? I have not tried this model many times, but what Sir has told is it works reasonably in practice. That's what he's saying. Okay, so maybe you can take few data sets and see whether this works out. Okay, yeah, but why we are doing this model here is this assumption. Now, because we are making this assumption, we are able to get out of the computational infeasibility, right? This is not possible computationally, but the one which differentiates this model and this model is this class conditional independence assumption, right? Am I right? So so this, I mean, this assumption is crucial for what? For this model being computationally feasible. Okay. For you to, I mean, run this model, this assumption is necessary. Okay. So that's why we are going to follow this one now. Okay. All right. So that's the thing. That's why we are going to follow this. So this is about the class conditional independence assumption. Okay. So this one you can go through again. Now likelihood function. Okay. So what we have to do is, now these are the parameters. We don't know what the parameters are. Okay. Maybe I can write what the parameters are. So the parameters are, you have P. I think it's explicitly given here. Maybe I'll not, maybe, I mean, you can get what the parameters are, right? So this P and all the P's here, right? So these are the parameters. We don't know what the parameters are. So one simple way to estimate, I mean, one general way to estimate is maximum likelihood, right? So what does maximum likelihood say? For which I mean, it is, you're going to maximize the likelihood function. So likelihood function is like this. For different parameters, it's going to plot the likelihood, which is given by either PDF or PMF, right? So for different values of parameter, you're going to have different likelihoods. And for which set of parameters are you going to get the maximum likelihood? That is what is being estimated by maximum likelihood, right? So that's what we are going to do to estimate the parameters. Now, if you look at this, what we are trying to model at the end is P of x comma y. Okay, which is given by P of x given y into P of y, right? That is what we started with, right? That is given by this. Now, what is this? What is this? So P of x given y, because of class conditional independence assumption, is given by this, right? Because of class conditional independence assumption, it's given by a product of all these things. So this is for feature 1, this is for feature 2 up to feature D. Okay. So for all the features, now we'll put it as feature 1 to D. Okay. J is going from 1 to D as a product. So J is from 1 to D. Now what is going to be within this? It's going to be this one, right? It's going to be this one, but you don't know what the feature is. Can either be, now this is for P of Fi being equal to 1. but it can also be 0, right? It can also be P of Fi being equal to 0 given y is equal to 1, which is nothing but 1 minus this one. Okay, so that is going to be given as this expression. Now this is for one data point. Okay, so this is for one data point. Okay, so if you look at this carefully, now let's look at this one alone first. Okay, if you look at this one alone. Now for every feature, what it is doing is, now Pyj, now this y can either be 1 or 0. Maybe for simplicity, maybe I'll write it as 1. Let's say, let's write for simplicity, let's write it as 1. Okay, so this is given by, now for 1 it is given by P1j power Fi to 1 minus P1j power 1 minus Fi. Okay, now into, of course, now because y is 1, this is going to be 1 and this is going to be 0. So if you're training data, I mean, so this is going to be 1 minus 1. So if for a particular data point in your training data, if the label is 1, then this will be equal to P power 1, which is P, times the product from 1 to D, this expression alone. Alright. Fine. So what you are doing is P1j power Fi. Okay, I'm sorry. This one will be like this. This will remain as it is. So only this one will change, but this one will also change depending on the email. Okay. So let's say the email is 0111010. Okay. Now what this entire expression will turn out to be is, you'll have P. Now within this, the product will be like this. Now since your feature is 0, this will turn out to be 0 and this will turn out to be 1. Okay. So this will be 1 minus, now this is for the first feature, right? So this is for the first feature. Right? And for the second feature, it is 1. So for second feature, you are going to get this one. Okay. So this is for the second feature. Alright. So for the third feature also it is 1. Okay. So for the fourth feature is 0. For the fourth feature, this is 0. And for the fifth feature, you are having 1. Maybe we can copy this. Okay. For fifth feature, you are having 1. And for the last feature, you are having 0. Okay. Fine. So this is just a multiple of all these things. Okay. So this is going to be P of x and y. So this is P of y being equal to 1. Now if the label is 1, you will have this one, because because y is 1, so 1 minus 1 will become 0, so you'll have this part alone. Okay. And the powers are all 1 because the label turns out to be 1. Right. So this is for feature 1, feature 2, feature 3 up to feature 6. Okay. So this is what this turns out to be. Okay. So this is the expression. Do you want this or can I erase this? Maybe I can erase this.
Yes, sir. I guess you can leave it, sir. You can write somewhere.
Okay, fine. No worries. Right. Okay. Now the likelihood function. Okay. So for one data point, P of x comma y is given like this. Okay. Then what will the likelihood function be? Okay, let me write y is equal to 1 also. Okay. So if for one data point, P of x comma y is given by that product, it's given by this product, then the likelihood function will turn out to be what? It's going to be a product of everything, right? See, now forget about not about the features, but at the beginning itself, in week 4 itself, what the assumption which we have made is the data points are identical and independent, right? IID, they are assumed to be IID samples, right? The data points. So based on that assumption, so this is going to be a product of these things. Okay. Alright. So the likelihood function, the parameter is theta, which is all these parameters, all these 2D plus 1 parameters. Now this also has an input of data. Okay, the data points. So for now this one is given by this part, which is taken from here. This is taken from this. Okay. It's okay. So this inner part is taken from this one here, and you are going to have it as a product for all the n data points. Alright. You are going to have it as a product for all the n data points. Fine. So this is the likelihood function. What we have to do is again maximize this and find the solution. Okay. So can we maximize the likelihood or what? So here if you notice I have made one small change. So here it is just fj. Okay. Here it is just fj because for one particular data point feature j is understood. And you have n data points, right? You have n data points. So I've written it as fij. Okay. So this is for the ith data point and the jth feature. Okay. So that's all, not much difference. Okay. All right. So this is the only small change which I have done. So this is the likelihood function. Now what we have to do is we have to maximize the likelihood and we have to get the solution. So can we maximize the likelihood or is the solution enough for you? What I'm asking is, do you want me to take the gradient and those things now? If you want, we can do, otherwise,
If
we can go. Sorry?
you can explain, sir.
No, your voice is not clear.
You can explain it, sir.
So what we have to do is, now for maximizing, we'll take the log of that. Okay. So for maximizing, we'll take the log likelihood. Okay. So let me copy paste this one here. So when you take the log of this is going to be this product, instead of product, this is going to be sum first. It's going to be sum from I is equal to 1 to n. Okay. Now within this you will have log. Okay. So within this you will have log. So what we will do is we will separate it as plus and all like that. Okay. So you know, right? Log of AB is equal to log of A plus log of B, right? So log of AB is equal to log A plus log B, right? So we'll do that. Log here. Maybe I can remove this. Log here. So plus log here. Plus log here. So plus log here. Okay. So I mean here this was one product big. This was one product and this was one product. Now this entire thing was product, so it became sum of logs. So within the log itself, you have separated. Now for every data point, you have all these sums. Okay. Here is the first step clear. For every data point, you're going to have all these sums. Okay. Now what we will do is we will split these things. Okay. So we'll split these things. That is, the summation is there, right? We'll add the summation for everything. Okay. Let the summation be there for everything. Okay. Alright, it's a sum of three things. And you have some here, so that can be splitted out. So if you look at this is going to be yi. So log P, so this is going to be yi. Now this yi will come here, right? So this yi will come here. Okay. And similarly, this 1 minus yi will also come here. Minus yi will come here. One second. Yeah. Right. And now this one. So now inside this log you have another product. So this can again be written as summation. Right. This can again be written as summation. J is equal to 1 to d. But this log will go inside. Okay. So this log will go inside. Got it? So what I did was, now first itself you could have done this. Now when you took log outside the product, that log went inside, right? Similarly for this log will go inside this. So you'll have log for here for this one alone. Okay. Now this can again be written as sum of sum, right? You have product, so you'll write this as sum. Okay. Now one thing. So now this ya is a part of notation and this fij is the number. Okay, so you should not multiply these two. Okay, so here you should not multiply these two. Here this ya is a notation. Alright, but here this ya is not a notation. Okay, so here this ya is the value itself. Alright, so what I'm saying is, so this here it is p power 1 to 1 minus p power 1 minus 1. So that is here. So this y corresponds to this one here. Whereas this notation here, if you see Pyi power Fij. Okay, so you should not multiply these two things because this is like P11, that is like P11. Okay, so P11 power feature. Okay, so you should not multiply these two. Okay, so just for your observation, I'm just saying. Okay, so this plus log of this one. Okay, so if you do that, this log will come, in the power will come here. Similarly, this power, it will come here. This one will come here. Okay, fine. Now what we can do is, we can write the same thing. We can multiply these things basically. Now with 1 we'll multiply this, and with minus y we'll again multiply. Okay, this one can. Hey, is the steps clear till now? Are the steps clear till now?
It's clear.
Let's pause if we are not getting anything in between. Okay. Now, so why I have done this is, now in one part I'll have 1 alone, and in another part I'll have minus y alone. Okay. So when you multiply this with 1, you'll have log 1 minus p itself. So let that be as it is. Okay. Now this minus, it will go outside. Okay. So basically you have sum of, so you have yi log p minus yi log 1 minus p. Right. So you have these two things. Maybe as of now, let's keep it like that. Now this one. Okay. Okay. So this, what we can do is, okay, let's keep it as it is. Now let's say we differentiate for p. Let's first differentiate for p alone. Okay. So if you differentiate for p alone, now for differentiating for with respect to P, what you need is, you want to differentiate with respect to P, you only need these three things, right? These things are not necessary. Okay. So by differentiating with respect to P, ultimately you have gradient. That gradient will have 2D plus 1 2D plus 1 features, right? So now one of that feature is P. So for differentiating with respect to P, what you need is only this part. Okay. So for differentiating with respect to P, what you need is just this part. Okay. Now this, what is this P? P is going to be some same thing. So this log P will be the same for all the data points. Okay. So this log P can come outside. Okay. So similarly, this log 1 minus P can also come outside. Okay. Now summation of this for all the data points is going to be n log P. Okay. So this is going to be n log P. Alright. Clear? I mean, what I'm saying is log P is going to be the same for all data points. So that will come outside. Similarly, log 1 minus P is same for all data points. That also came outside. And log 1 minus P, this is a constant. You're adding it for n times. So this is going to be n times this. Okay. Alright. Now, what is this? What is this? What is this? So if you're adding all the labels, what you're going to get? If you're going to add all the labels, you're going to get the number of labels with feature ones. Okay, so let me write it capital N1. Alright. So this is also capital N1. Okay. Now this is easy, right? So now you differentiate with respect to P. You differentiate with respect to P, you will get N1 by P, okay, minus N1 by 1 minus P. Now you have to differentiate 1 minus P also. So that will make this plus.
Plus.
Okay. And so this will become minus. So this is total number of data points by 1 minus P. Clear? Now you equate this to 0. To equate this to 0, this will become, now this, let us keep it here. Let us keep this one here. Let's make this to be equal to, now this will become plus on the other side, this will become minus on the other side. Okay. So this will become n minus n1. Okay. Now let's multiply everything. So you're going to get n1 minus npn1. Okay. So this will be equal to np minus pn1. Okay. So these two are equal. Okay. So these two are the same. So those will cancel out. So n1 is equal to np. So p is nothing but n1 by n. All right. So which is your fraction of ones. All right. So this is nothing but your fraction of ones. Right. Which is given by summation of yi. You're adding it for, you're adding the labels of all the data. Okay. Which is your fraction of ones. So I is equal to 1 to n. All right. So did you all understand? All right. So this is for fraction of data points. Now what you should also estimate is p power for the ith data point feature j. Okay. So this is what you should estimate. Now this, if you want to estimate this one, let's say you want to estimate p11. For the first data point, you want to, okay, extremely sorry. So Pij is what? Pij is equal to, I mean, not equal to, let's say we look for a particular case for label 1 and for feature 1. Let's look at this one alone. I mean, like this one you have to do, right? For label 1 and feature 1. Label 1 feature 2 up to label 1 feature D, that you have to do. Similarly, label 0 feature 1, label 0 feature 2 up to label 0 feature D. Okay. So for this one, what do we need? For this one, what you need is you want for label 1 and you want for a particular feature, right? Now a particular feature f1 is given by this, what is there within alone, right? For a particular feature, whatever is there within is given, right? But you want it for all the data points. Okay. So I mean, now if you know, let's look at this one. Let's look before looking at this one, let's look at one more thing. So this can be written as, this is just the same as this summation going inside, correct? Am I right? Yes. So ultimately everything is addition. You write a plus b or b plus a, everything is going to be the same, right? Alright. Now for every feature, you're going to sum for all the n data points, right? Alright. Now you want for a particular feature. So if you want for a particular feature, you will take this one alone. You take this one alone. And let's say you want it for feature 1. I mean, you want it for label 1. You want this for, now you're trying to predict for feature 1. So this j will be 1 here. J will be 1 here again. J will be 1 here again. J will be 1 here. And the label will be 1 again, right? So 1. Alright. Right. Now, so this, how will you write? Again, you can write this summation. You can split the summation first. So this summation can come here. Alright. Is that all we have? Now here, this one is a constant. Okay. So this one is a constant. And this one is also a constant. Right. So these two can come outside and these two can come outside, right? Fine. So these two will come outside. Now, if you look at this can again be split into two things. This will be, you can split this again into two things. Okay, so this one will be here, and for this also it will come. Okay, so if you split this here, you are going to get, I mean, this is common for both. So let's split that. Okay, so copy this, paste this here. Clear? Fine. Now, what is the first one? What is the first one? The sum of, now for all the data points, you are summing the first feature. You look at this, for all data points, you are summing the first feature alone. Right? Fi1. For the ith data point, the first feature. Right? So what is that going to be? Now the features are binary. What will that be? Let's say you have four words, which is 1 0 0 1. Okay, and 1 0 1 1 and 0 0 0 0. Maybe it's 1. At last, let's say 1 0 0 0. Now for all the data points, you are summing the first feature. So what you will get is 3, right? Which is the number of data points for which the first feature is 1, right? Which is the fraction of emails with these words, with the first one, right? So let's write it feature 1. Feature with 1 represents that the value is 1. The number of data points which feature being 1. Okay. So if this is here. Now again you have this one. And you're summing 1 for all the n data points, you're going to get n log 1. Okay. So minus, again, you're summing this again. Now this one is again the same thing, right? So this is F, sorry. Okay. This 1 should be I. Okay. Yeah. Okay. So this will again be NF1. Okay. So if you differentiate, you are going to get NF1 by P11, which is, it's given that it's a spam, and for feature 1, the probability of that point crossing to head. Okay. So plus N by this, and if you differentiate
Minus.
this one, you will get minus. So plus, again you will have NF1 by 1 minus P1. Okay. And yeah, you have now this minus became plus because you differentiate this also. You equate this to 0. Now this looks like just the same as the other, this one, right? This looks just the same as this one. Exactly the same as this one, right? Just the same as this one. So for these two, it's going to be plus, and here it's minus here. Same thing here. Okay. So what this will turn out to be is P11 will be equal to NF1 by N. Alright. So the same thing in the last one, but things, I mean, this NF1 and all those things have changed. Okay. Fine. Alright. I mean, you can go through this again later, but why I did this was maybe for other cases you can work it out, right? So that's why I did this. So if it's fine, we can proceed. Did you all understand? I mean, like if you are not, if you immediately can't do, it's fine. But in every step if you are able to follow, you can, it's fine. Okay. So even if you don't know this is fine. But the optimal solution turns out to be like this. Okay. Now the same thing you will do for other coins also. This we have done for one things. There are 2 power d, or you are not going to do for everything. For one thing I have done, for other things also it's going to be the same. Okay. So, but optimal solution intuitively, if you want to know, the p hat is nothing but the fraction of ones. Okay. The fraction of ones, the number of ones divided by n, which is the fraction of ones. Okay. And what is Pyj? Okay. The fraction of data points. I'm sorry. This is going to be now Pyj is going to be fraction of data points. Now this is the denominator is the number of data points with label being y. Okay. Okay. Once again, maybe I can put this in a diagram. Okay. So let's say these are the set of all the data points with label 1, and this is set of all the data points with label 0. Now let's say you want to estimate P11. So this one we have seen there, but in terms of this, what I'm trying to say is, so this is set of all the data points with feature zeros. This is set of all the data points with feature 1. Now, I'm sorry, with label 0, label 1. Now among label 1 itself, some data points, for some data points feature 1 will be 0, and for some data points the features will be 1. So what this P11 is capturing is the number of data points here, which let's call this A, let's call this region B. Now what this P11 is trying to do is it's trying to find A by A plus B. Okay. So A by A plus B. Now A plus B is what? A plus B is the number of data points with label being 1. Okay, number of training data points with label being 1. That is A plus B. What is A? Now the label should also be 1. Label should be 1, and the feature should also be 1. Okay. So those the number of data points there is coming here. All right. Fine. So that is what is given by this thing. Clear? Is it fine? Many people have left. Okay. Is there any, I mean, is the teaching not okay or is there any doubt? Yeah. Is there anything, I mean, like many people have left, so that's why I'm asking. Is it fine? Are you able to understand or what?
It is fine, sir.
Okay. So this is, you'll, I mean, this one, if you have to repeat, if you want P11, you'll go to class 1. The denominator will be number of data points in class 1. And the numerator will be the number of data points in class 1 with feature 1 being 1. Okay. So here, if you want to know if there are 4 data points with class 1, so all these are in class 1, then this will be 3 by 4. Okay. That's all. All right. So that's all is being done there. All right. So this is the solution. This is the way to interpret the solution. Okay. Now, how will you predict? So next thing is how will you predict? Okay. So the prediction is given by this, right? Ultimately, if you want to predict, what you have to do is, so given a test data point, if the probability that the label of the test data point being 1 is greater than the probability of the label of data point, I mean, so this is what, so given a test data point, what is the probability that the label is 1, right? That is this one. Now this is what, given test data point again, what is the probability that the label is 0? All right. So these are the two things. You will calculate these two, you will compare, and you will see whichever is greater, you will have that as your prediction. If this inequality is true, then you will predict 1. This inequality is false, then you will predict 0. Okay, that's all. Fine. Now, again, this can be written as the following. Okay, so you have P of, now you know one thing, right? P of x comma y, it was given by two things, right? P of x into P of x given y, and P of x into P of y given x, and it was also equal to P of y into P of x given y, right? So these are the two things. Now what you want is, let's have this part alone. What you want is, you want this one. So what you will do is, you will take this to the denominator here. Okay, you will take this to the denominator. Now you know how to estimate this one, and this, if you see, will not be important, because for feature 1 also you are going to have P of x on the denominator. For, I mean, for label 1 you are going to have P of x in the denominator. For label 0 also you are going to have this in the denominator. So this will cancel out on both sides, and what you will end up with is P of x and y. Okay, so that's what you will end up with, and that is something which you have already modeled, right? You know what the optimal solutions and all those things you know, and it turns out to be this. Okay.
Sir, can you please show your last example you have calculated, sir?
Yeah.
In last example, you have calculated that 1 by 3 by 4, I think. From this, yes, sir. How is it was calculated, sir?
So what I'm saying is, let's say you have, okay, let's say the labels for the first data point is 1, second data point is 1, third data point is 1, and fourth data point is 0. Okay. Now, what you want is probability that the mail is spam. Now, for a mail, if that mail turns out to be spam, it's what I'm saying is, if it is given that the mail is spam, what is the probability that this mail will have the first word? About other things, not now, but for this one alone, let's look. Okay, so this is given by P of 1 1, right? P of 1 1. So this will be, now you will first find the number of data points with, you will first find the number of data points with label being 1, which is 3. Okay.
Okay, we are doing based on this first word only, right?
First label being one. Label being one. And among the label being one, you
The
look
first
at three
first
data
word.
points. Yeah, the first word. Now for the first word, this is one and this is one. The third email does not have one. So you'll have 2 by 2. Okay. All right. You have 3 emails, and among those, I mean, you have 3 spam emails in your training set. Among the 3 spam emails, 2 of those emails have the first word. So this prediction turns out to be 2 by 2. Okay.
And all these emails out of these four, three are from spam and one from non-spam class, right?
Ah. Now
So when
if you want P01,
okay,
what will that be?
that is
You
on
have
the
one data point. You have one data point. I mean, you have one data point, and the feature turns out to be 1. Okay, so you'll have 1 by 1. So this probability will turn out to be 1. Okay.
so that only one word which we are estimating is making this whole email spam, right? Sir?
Yeah, just because you have only one training data point, it turns out like this.
Okay,
Okay.
thank you.
Yeah. All right. So this is the thing. So this is how you'll predict. Right? Maybe this can be there. No. Now the prediction, as I told you, P of y equal to 1 given x test. If it is greater than P of y equal to 0 x test, if this inequality is 2, you'll predict 1, otherwise you'll predict 0. Right? Now turns out to be that turns out to be P of x test comma y test itself. P of x test comma y test being equal to 1. This should be greater than P of x test comma y test being equal to 0. Okay. Yeah. Yeah. Is there any doubt? Hello. Is there any doubt? Okay. Fine. All right. That is basically from this. Okay. So we have just rewritten this. Base 2, we have rewritten this. And the denominator on both the sides are same. So we'll cancel out that. And you're getting this. Okay. So this we already know, right? This one we already know. We'll estimate all the parameters. But this F, we'll estimate all the parameters. But this Fj, what is Fj? Feature j. Okay. This feature j, 1 minus feature j, that alone will come from the test data point. Okay. For example, if your test data point, let's say you're training, you have learned that p is equal to 0.7. And let's say you have 2 features. And p11 is equal to 0.3. And p12 is equal to 0.5. Okay. And p01 is equal to 0.8. And p02 is equal to 0.1. Okay. You have 2 features, and you have, so 2d plus 1 is 2 2s are 4, 4 plus 1 5. So 5 parameters are there. Okay. So let's say if these are your 5 parameters, okay, and your test data turns out to be 0 1. Let's say if this is your test data point, then probability of y test being equal to 1 given x test will be equal to, now p hat is what? P hat is 0.7. So points, yeah, 0.7 into P1j power Fi. So what is P1j? P11. No, okay, I'll write it like this. Okay. So this is going to be, one second. This is going to be P11. Now your feature is 0, right? The feature is 0. And 1 minus 1 minus P11 power 1. Okay, so this is 1 minus 0. Okay. So this means if your feature is 0, you will pick 1 minus 0.3, which is 0.7 again. 1 minus 0.3 times next P12. What is P12? P12 is 0.5. Now your feature 2 has 1. So this will become P12 power 1. Okay. So P12 power 1 and 1 minus P12 power 0. Okay. So which means you'll have 0.5 itself. And similarly, so this is going to be, you will multiply all these three things. Now this is for P y test being equal to 1. Now you should also look at it for P y test being equal to 0. Now for that you will have 0.3 here. Now times, since the first feature is 0, you will have 1 minus 0.8, which is 0.2. Okay, 1 minus 0.8. And for second one, since the feature is 1, you will have 0.1. Okay. Okay. So this is how you will predict. Now you will multiply these two and you will see which one is greater. Doubt in activity question 6, 8.3. Okay, I'll come to that. So first, is this one clear? Is prediction clear?
Yes, sir.
Yeah. So this is how you'll predict. Basically, you just substitute it in this formula, but maybe, I mean, you may not remember this formula, but if you know how all these things are working, you can directly look at the data set and all right. So this is how
Can you
the
once repeat
yeah
how you are substituting this
yeah.
F
So
I
basically,
and F I J?
yeah, basically now this is there within the product, right? So this is there within the product. Now for all the features you have to look. You have to look for feature 0 and feature 1. Okay. So you first, now for P of y, now probability that y test is equal to 1 given x test will be given by, first you take 0.7 itself. You multiply that, now you have 0. That is the feature, I mean that word is not present. So this will be 1 minus that, right? Just because the power turns out to be 0 here and 1 here. So you'll have 1 minus that, which is 1 minus 0.3, which is 0.7 again. And for the next one, since the feature is 1, you will have 0.5 itself. Okay. So when you multiply all these three, you're going to get this one. And for this one, what you'll do is, now you want this to be equal to 0. You want to check the probability for that. So that will be 1 minus 0.7, which is 0.3. Okay. Now since the first feature is not there, it will be 1 minus 0.8, which is 0.2. And since the second feature is there, you will take 0.1 as it is. Okay. Fine. So if a data set is given like this, and if the predictions or if the parameter, if the value for the parameters are given like this, the prediction will be like this. Okay.
Yes, sir. Thank you.
Yeah. So this is how you will predict. Okay. Now there's something called as Laplace smoothing. Okay. So what Laplace smoothing does is, what happens is sometimes, now the feature, let's say you have for some word, let's say for the last word zebra, for example. Let's say for the word zebra, there's no email in the training data with the word zebra, right? If there's no email in training data with zebra, then this fraction will become 0 here, right? Then this fraction will become 0, all right? So if that fraction becomes 0, then now this I is for the ith feature, but for the last feature, this will be 0. If for the word zebra, this will be 0 for the last. Okay. So these two things are 0. All right. But if your test data point has the word zebra, see the feature is this one is 0. But if for the test data point, if the feature is there, okay, then what happens? You will have 0 power 1 and you will have 1 power 0, right? Because the feature is there, which is I mean, the feature is there. So this will be 1, but this will be 0. And since this is 0, this will be 1, but this will be 0. Right? So 0 power 1 is 0. So this product will be 0. Similarly, for second one also, if you look at this, it will turn out to be 0. Okay. And overall, if you look at this one, this is a product of everything, right? It's a product of everything. Even if one of this becomes 0, then the entire thing will become 0. Okay. So you'll have 0 greater than 0, which means you are not going to make any meaningful prediction. All right. You're not going to make any meaningful prediction. Fine. So the issue, basically the issue is training data point does not have feature I, but the test data point has feature I. Okay, that's the issue. So what you will do is you will do Laplace smoothing. So what Laplace smoothing does is you'll take an email. Okay, you'll take some email. That email will have all the words. You'll have all the words. Okay, you'll take this email and you'll add it to your training data. Okay, so this with the label 1 and with the label 0. So you'll have two emails. Okay, you'll have two emails. So one with label 1 and the other with label 0. So you're going to add two emails. All right. And for these two emails, these two will ensure that these two are not 0, right? So if these two are there, then fraction numerator will at least have 1. Okay. So because of that, it will not become 0. Clear? Fine. So basically, you don't want your when you go and predict, you don't want both the sides to be 0, which will not help you to make any meaningful prediction. So what you do is in your training data, just add one email. So maybe you're going to have 10,000 emails. You're going to add one more email. It's not going to cost a lot. I mean, it will not disturb the setting much. Okay. So you'll add two emails, one with label 1 and one with label 0. So that for all the things, the prediction, I mean, the probability is not completely 0. Okay. So this is called as Laplace smoothing. All right. Clear. Now there's one more thing. Is it clear? Is Laplace smoothing clear?
Yes, sir.
Yeah. Okay. Now, at last, for naive Bayes, we have one more thing. Okay. So what we have at the last is the decision boundary. Okay. So what is a decision boundary? Let's look at algebra once again. Okay. Just for one more time, we look at algebra. For Gaussian base, maybe we need not look at it. Okay. What we'll do is let's look at these two things. Let's look at these two things. Now, when you take log, the inequality will not change. Okay. If you minus this, then the inequality will reverse, right? That will not happen if you take log. Okay. If you take log, the inequality will not change, which means your prediction will still be the same. Let's take log on both the sides. Okay. Or maybe, yeah. If you take log on both the sides, what you will have is, okay, you can take log here or you can take it afterwards also. Once again, let's do one more thing. Let's take this and let's put it in the denominator. Okay, we'll put this in the denominator and this will be 1. Now we'll take log. Otherwise also you can do, but it will be more work. Now we'll again take log. If you take log, what will happen is, again you have to add. These products will become sums, right? So first, just bear with me for one more time. So first, what you will have is, you will have this one here. Okay. All right. So this one will come here plus log. Okay. Now the numerator will have this product. The denominator will have this product. All right. Now these two are product of the same things. So what we can do is we can take the product itself as common. All right, everything is multiplication and division. So instead of having two separate products, let's have one product alone. Okay, clear? Now these are all products. Now log of this will be make it sums, right? So log of this will make it sum. So sum from I is equal to 1 to D. Let the log go inside. Alright. So when the log goes inside, now this will product will become what? Sums. Okay. So what we can write? We can write the same thing as, now this one will come here. One will come in the denominator. So this plus once again log. Now you will have this one in the numerator and this one in the denominator. Okay. Right now we can get rid of this. Clear? Right? Now, now this Fi is same for both. Okay. So this Fi is same for both. So what we can do is we can write Fi common. We can take Fi to be common. So power Fi, feature I. Fi is what? Feature I. Okay, you have D features. This is feature I of the test data point. Okay. Now you are predicting for your test data point. Okay. Now this is feature I of test data point. Okay. So similarly, you will have. Let me copy this here so that I can just change the numerator and denominator. Similarly, you will have 1 minus P0 and 1 minus P1. Okay. And the numerator will become 1 minus Fi. Okay. So you can get rid of this. All right. Now, since this is log, the power will come to the other side. So Fi will come here. All right. And this 1 minus Fi.
Sir, it is Fi or F1, sir?
Fi. Sorry. Fi will come here. And 1 minus Fi will come here. Okay. One minus Fi. Okay. All right. Now, so at last we can do one more thing. Now this one is there, right? So this one is there, right? So 1 times log will become the same thing. And you have minus Fi. You have minus Fi times this. All right. Clear? So what I have done is there is something common outside. I have just splitted it. Okay. So 1 will make it as it is, and minus Fi will make it as it is, like this. Okay. Now you can do one more thing. Now this Fi is common. So what we'll do is we'll take this here. We'll take this one alone inside. So we are mostly done. Okay. So we are mostly done now. Okay. Last thing, the summation is there, right? So the sum of two additions. So let's take this, let's make this summation also come here. Okay. Fine. All right. So now let's call this constant. Now this is going to be a constant thing. Let's call this C. All right. So this will be C. And now if you notice, now for every I, I is equal to 1 to D, right? For every I, sorry, this is going to be J. Okay, now this I and J are same, okay? I'll change it later, but this I and J are same. By mistake, I think some confusion as well. Okay. So this, it is J, but by mistake I've typed high here. Okay. So this is going to be J, but by mistake I have written I. We'll change it. Okay, this is going to be J. Yeah. All right. Now let's write. Fj, okay, Fj, and this one for all j, this is going to change, okay. This one put together for all j, it's going to change. Now let's call this then Wi, Wj. Now this is going to be equal to Wj, okay. Now plus this is again some other constant. It's not constant, it will change, but in the context of this one, this part, it's a constant. It will, okay. So this is another constant k. So this will be equal to this plus some b. Okay, now this
Sir,
k plus c is
how
going to be
how it is W, sir?
so this Wj is equal to this part. Okay. So Fi multiplied by something, correct? That multiplied by something is this Wj. Alright.
Is it some vector, sir?
No, this is some real number. Log of something minus log of something else. So this is a real number, and this Fi feature it's 1 or 0. Okay.
Okay, Fi is also one dimension, and this is also constant.
Yeah. So this is multiplication of two real numbers.
Okay.
And these are, and in the context, this is, you can take this as some constant and you can take this as some other constant. Okay. You add c and k, you'll get some b. So this can be written as W transpose. So this is nothing but W1 dot WD dot product with feature 1 dot feature b. Okay. So plus b. Now this can be written as W transpose X test, right? This can be written as W transpose X test. Okay. So W transpose X test. So plus b, which means now I have not written one thing. I have not written the right hand side. Okay. So this is the left hand side. Right hand side is log 1, which will become 0. This should be greater than 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 0. And this should be greater than 0. Which means for, if I have to put this now diagrammatically, I'll quickly write this. 1 second, please. So let's say this is in 2 dimension. Let's say this is x axis and this is y axis. Okay. And let's say W transpose X plus B is some line. Okay. And W is some vector. And W is some vector. Now that vector you can learn, right? So W is some vector. So which is given by this. Okay. Now you want, now when will you predict? Now if this inequality is true, you will predict 1, right? What does that basically mean? This inequality is true, you will predict 1. So that basically means if your data points are on this side, your data points are on this side, you will predict 1. And if the data points are on this side, you will predict 0, correct? So that is what this is. Okay. So this is W, and this line is your, it is the demarcator of your decision boundaries, right? So which are, if a data point is here, if your test data point is here, the prediction is going to be 1. If the test data point is here, the prediction will be 0. Okay. Any doubt?
Sir, if it is online, then
It's online, then we have to decide. Basically, tiebreaker, we have to decide whether it's 1 or 0. That maybe will be given on question. And
okay. It
if
will
you
be
like the
given.
model, you will decide. Okay. So that we will decide, but I mean the decision boundary has a linear separator. Okay. The decision boundary is linear. Okay. So this is the takeaway. You have to summarize everything. For naive base, the model is like this. You will flip a coin. Prediction is head or tail, spam or not spam. If it's a spam, for every feature you will flip one coin. Okay. And based on that, you will generate the email. Similarly for not spam. Okay. So there are 2D plus 1 parameters. Okay. There's a class conditional independence. That is, the presence or absence of one word does not determine the presence or absence of any other word. Okay. Now, likelihood function is given by this. These things you can go through. So when you maximize the likelihood, the prediction is like this. P hat is fraction of class 1 labeled data points. Now Pyj is given like this, or P11 is given like this. You'll go to class 1. You'll take all the data points in class 1, put it in the denominator, the sum, the number of data points in class 1, that's the denominator. The numerator is among class 1. You'll see for whichever data points the feature is 1. You take that and count the number of data points, put it in numerator, find this fraction, that is going to be P11. So similarly, you will calculate for other things. Okay. Now, how will you predict? The prediction is given by this. P of y equal to 1 given x, it should be greater than P of y equal to 0 given x. And that is given by this. Okay. Which turns out to be the one which you model. P of x comma y and P of x comma y is equal to 1 and P of x comma y is equal to 0. So you'll see whichever is greater, you'll predict. And how to predict? There's an example here. Right. So how to plug in the values? There's an example. Maybe we'll do it. We'll solve some questions. Now, Laplace smoothing is basically done. Like if you don't have any, if the training data points does not have some word, then the multiplication will become 0 if that word is there in the test data point. To avoid that, you'll have 1, 1, 1, 1, 1 with label 1 and label 0 in your training data point, and then you will learn. Okay. And the decision boundaries linear. Okay. So this is the overall summary. Fine. This is for naive base. Understood? Sorry, someone asked a doubt in between, right? I'm sorry. Yeah, now I'll come to this. Okay, so before that, is it clear?
Yes, sir.
Yeah. Yeah. Hello.
Mm.
Yeah, you asked some doubt, right? So activity question 6 in 8.3.
It,
Yeah,
yes, sir.
Yeah, we'll look at that. Okay. Now activity question number 6, right?
Yes, sir. Question number
Okay.
6.
Fine. So using naive Bayes algorithm, what will be the prediction for label 0 or label 1? Okay, maybe we can solve this question. So what? Maybe we can look at Gaussian Bayes tomorrow. Okay, tomorrow and the next class. Let's solve this question. Okay. Like a classic question for week 8. Yeah. So now consider a binary classification with 4 binary features. Okay. The labels follow uniform 0, 1. Okay. Now the training data set contains the following 4 points. Okay. Now your features are binary, but the labels are 4. Sorry. I'm extremely sorry. Extremely sorry. Now what the question is saying is consider a binary classification problem. So you have 2 classes. Now there are 4 features. Feature 1, feature 2, feature 3, feature 4. They are binaries. Now the labels follow uniform 0, 1. Okay. So uniform 0, 1 is probability for 0 and 1 both with 0.5. Okay. So probability of y is equal to 1 is going to be 0.5. Probability of y being equal to 0 is again 0.5. Okay, so this is the first thing. So next thing. So basically what we have to do is we have to compute this one. Okay. We have to compute the optimal solution. Okay. We have to compute these two. So these two. Okay. So the first one is done. Now for the second one, so what you have is you have 4 features, right? So you have 4 features. So what are your things? So how many parameters are there? 2 times 4 is 8 plus 1 9. So you have to estimate for 9 things, one of which you have done. You have to do for the remaining 8. Okay. So what is P? Now label is 1, feature 1. So what will that be equal to? Okay. So the labels are 0, 1, 1, 0. Okay. So let's look at label 0 and label 1 data points. So label 0, the data points are given by 1, 0, 1, 0. Okay. So you have 1, 0, 1, 0. And label 0, the other data point is 0, 1, 0, 1. Okay. 0, 1, 0, 1. All right. Now, this is for label 0. And for label 1, what are the data points? 1, 1, 1, 0, 0, 0, 1, 1. So 1, 1, 1, 0 and 0, 0, 1, 1. Correct? Yeah. Now, so how will you predict? So P for feature 1. So this will be, so how many label 1 data points are there? 2. And for first feature, you have 1. Okay. So this is 1 by 2. Next. P 1, 2. So how many label 1 data points are there? 2. And for feature 2, again, there is 1. Okay. Now, P label 1, feature 3, you have 2 data points again. And this time, all the both the data points have feature. I mean, both the data points have the same feature, right? And it is 1. So this will be 2 by 2. And for the last one, sorry, P label 1, feature 4, this is going to be 1 by 2 again.
1 by
Because
2.
1 is alone by. Okay. Now what we have to do is we have to do the same thing again for label zeros. Okay. So label zeros, the denominator is going to be the same because there are again 2 data points. Okay. Yeah. Now you have again 2 data points. So all the denominators will be 0 for label 0. Okay. Now for the first feature, again it's 1. So 1 by 2. Second feature, again 1, 1 by 2. Third feature,
Sir,
now it's going to be, yeah.
in this case, we'll have to look for zeros.
No. Label is 0. But
Okay.
still when you toss the coin, see, that's all. See, the label is 0. This part is 0. But still when you toss the coin, if it is 1, that word will be there. If it is 0, that word will not be there. Okay. Alright, so you still have to look for 1 only.
Okay.
If
Okay.
it is heads, it is still going to be 1.
But
See,
sir,
whether or
can
not
you scroll up, sir, little bit? Yes, yes. But here, Py square 0, it is 1 minus P.
no, that is so okay. So
Okay, oh, that is for P, sir. Understood, understood. That is
yeah,
for P.
okay, I'll just
Okay.
mention this. So this, what you are trying to ask is for this one. Okay, you are trying to ask this one. This will be given by 1 minus this one. Alright.
Okay, here we are finding whether that word is there or not. Right.
1 minus, okay.
Yes.
For that feature, whether that word will be there or not. So this coin is deciding whether the mail is spam or not. If it is a spam, what is the probability that this word will be there? And what's the probability that this word will not be there? I mean, not spam. Okay. And same thing here. Once again. Yeah. So this one will be 0 here. Okay. That is going to be 1 minus this one. All right. Fine. So, yeah. So these are the things. So these are the parameters. Once you have found the parameters, the only thing which you have to do is to estimate. Okay. So for estimation, so first thing, with what probability does the first feature take a value 0, given that the label is 0? Okay. So what it is asking is probability that the first feature will take value 0. It is given that the label is 0. So what will this
This is
be?
1 by 2, sir. 1 by 2.
Yeah, this will be 1 minus, no, in terms of notations, that is. In terms of notations, this is going to be 1 minus P, label 0, feature 1. Okay. So what is P0, 1 by 2? Okay. So this is going to be 1 minus 0.5, which is 0.5. Alright. So this notation
Can
is
you
also,
explain this notation one, sir? What
yeah,
notation you have
yeah.
written?
Yeah. So notation, so the question is asking for first feature, the probability that the value is 0 given that the point is labeled 0, right? So for first feature, probability that the label is 0 given that the email is said to be spam, or I mean probability that the features value is 0 given that the label is 0. So this will be what? So whenever there's 0, there's going to be 1 minus this 0. Now this 0 comes from this, and this 1 comes
Write
from feature
P
1.
first word.
Okay. All right. Right. So this 0 is coming and sitting here, and this 1 is coming from this one, feature 1. All right. So this is going to be 1 minus 1 by 2, which is 0.4. Okay. So using naive Bayes algorithm, what is the prediction for label 0 and label 1 for this data point? Okay. Now you have to predict for a data point 1010. Okay. So what you have to do is predict. What you have to do is now predict for 1010. Okay. So this is where you have to be a bit careful. Okay. Here also you should be careful, but here also. So what you have to do is you have to check if P hat, which is, you have to check if P hat times. Now if you look at that product, you go and yeah. So for every feature, you have to find this product, right? And copy and paste this there. Okay. Let me paste it here. So you have P hat on this side, and you have 1 minus P hat on this side. Okay. So now P hat is what? P hat, we predicted that. Now how many label 1 data points are there? 0.5, right? I mean, it is also, it's given that the label follows uniform 0, 1. So anyways, it's going to be 0.5. Okay. So 0.5, 0.5. Okay. Now, what is this going to be? So it's a product. Let's write it as product for every feature. Okay. So now you have 4 features. Now all the 4 features, let's have brackets. So for all the 4 features, put the brackets first. Okay. Now this is for label being there. Okay. So for these 4 brackets, you have to look at this one. And for these 4 brackets, you have to look at this one. Okay. Fine. Now for the first feature, is the first feature there? It's there. So what you do, you just pick 1 by 2. Okay. You just pick 0.5. Now, second feature is there? No. So you will pick 1 minus 1 by 2. Okay. Second feature is not there. So you will do 1 minus 0.5. Now, is the third feature there? It is there. So what you will do? 2 by 2, which is 1. So 2 by 2, which is 1. Now, fourth feature is not there. So we'll do 1 minus 1 by 2, which is 0.5. Okay. Here. Now here. Again, the first feature is there. So you go here. So 1 by 2. Okay. First feature is there. This is 0.5. Now the second feature there, no. So this is going to be 1 minus 0.5. Is the third feature there? It is there. So it's going to be 1 minus, it's going to be just 0.5 itself. And is the fourth feature there? It is not there. So this is going to be 1 minus 0.5. Okay. So now what you have to do is you just have to predict all these things. So if you look at this, this is 0.5 into 0.5 into 0.5 into 0.5. So this is 0.5 power 4. Is this greater than, now everything is 0.5 here, 0.5 power 5. Now you tell me which is greater. 0.5 power 4 is greater or power 5 is greater?
So power 4 is better.
Yeah, power 4 is greater because this is less than 1. Okay, so the prediction will be 1. Okay,
1.
yeah, prediction is going to be 1. All right. So let's check. For the first answer, it's 0.5. And for the second answer, the prediction is 1. Right? Yeah. Okay. Okay. So what you have to do is you write all the parameters like this. Then based on the data point, you apply one by one. Okay. So now this, there are too many parameters, too many notations, so you'll get confused. Okay. Understood. So you want me to solve any other questions?
You explain very well, sir.
Which one? Which one? No, your voice is not audible. I mean, it's audible, but it's not clear. So can you just type it? Thank you. Okay, so you are asking something. Fine. You want me to solve other questions? Any other question? You want me to solve some other question?
Yes, sir.
Yeah. Yeah, we can solve maybe some questions.
It is
Maybe 8 point.
8.1, sir. 8.1. So
8.1. Which question?
question number 5.
Yeah, question number 5. Okay. Consider a multi-class classification problem with k classes and d binary features. Okay. So k classes. Okay. D binary features. How many parameters will have to be estimated if we choose the generative model discussed in this lecture? So you have to look at the first lecture. The first lecture, that infeasible model was discussed, right? So k classes and D features. Okay. So k classes, D features. Okay. Now first thing, let's start with features. Okay, that is easy to do. Let's start with features. Maybe I can open this here. Yeah. Start with features. Now, if there are D features, how many possibilities are there? 2 power D possibilities are there. Correct? So this is for one thing. Now, usually for if you have binary thing, then you will have 2 arrows here, right? If you have binary thing, you will have 2 arrows here. There are 2 Ds. Because 2 power D minus 1 features, right? So you have to estimate 2 power D minus 1 for every feature. Okay. Now you have k things. Okay. So this is first arrow, this is second arrow. Now for third arrow, again you will have 2 power D minus 1. So like this, you have 3 arrows. So dot dot dot. Like this, you will have for k arrows. So one thing that you have to do is, so 2 power D minus 1 into k. That is one thing. And you have k classes, right? You have k classes. So probability of y is equal to class 1. Probability of y is equal to class 2. Comma dot dot dot. Probability of y is equal to class k minus 1. Comma probability of y is equal to class k. So you have these many classes. Now, if you know all these, if you can predict all these things, the last one can be 1 minus all these things, sum of all these things, right? So in terms of p of y, you have to predict k minus 1. Okay. All right. Understood. So if you look for our case, so it was 2 times 2 power d minus 1 plus 2 minus 1, right? So this is like the general formula, all right? So this is for infeasible story, right? Computationally infeasible story. So this, okay, I think they want us to expand. Okay, they want us to expand. Let's expand it. Yeah. So you have K classes. Okay. So this is K times 2 power d minus K plus K minus 1. Okay. So this will be K times 2 power d minus K plus K will get cancelled and you will have minus 1. Okay. So 2 power K times 2 power d minus 1. Okay. So I think it should be that. Yeah. Understood.
Yes, sir. Yes.
Yeah. So this part alone, I mean, this arrow mark you remember for the number of features, and this one, now this one is not difficult, right? 2 power d minus 1 is not difficult. Okay. So this is K minus 1 times 2 power. Okay. So next question, which one? Yeah, I'll share the PDF. So next question, which one do you want me to solve? Just randomly one more question we'll do. Let's say a binary classification problem with B features. Okay, this was already given. Right? Assume that we have modeled the distribution of labels for a given data set. We want to build a generative model for the same data set. Which of the following steps would be more appropriate? So what they are saying is, you would like to model P of x comma y. What you have modeled is, you have already modeled the distribution of labels, which is P of y you have already done. Now what else should you multiply to get P of x comma y? What else should you multiply?
P of x given y.
Exactly. That's what we were doing all these. I mean, for all these things, we are doing this. So what does this mean? So given a label, given spam or not spam, predict the email, right? Predict the probability of the occurrence of an email, correct? So models of features given the label, correct? So features given the labels. Okay. So the first one. Okay. So all the binary classification problem are binary. That is, they can only take two values. So should all the features be like it should take only two values? Not necessary, right? You can have real features itself. I mean, the features can be real numbers, which is what the Gaussian naive Bayes deals with, right? So this is not okay. Yeah. Okay. Let's look at decision. Yeah. So decision function of naive Bayes is linear. Now the decision boundary. Okay. Now in terms of set notation, tell the decision boundary for naive Bayes is given by what? What is the decision boundary for naive Bayes? Set of all x such that this one being equal to 0 or this being 0 or this being 1. So if this is 1, then this is like 0, right? And if this is 0, the other one is 1. Now, what does this decision boundary mean? At this boundary point, you have a tie, and on all the other points, there's no tie, correct? So at this point, there is a tie. So what does this mean? Set of all x such that the prediction is equal for both, correct? That's what it means, right? That's what the set means. The prediction turns out, I mean, the probability turns out to be equal. That's why there's a line here. And the prediction is, I mean, that is not asked here, but what is asked is, this is the set, right? This set will be a line. Okay. Now, next one. Is the decision boundary of naive base, should it always pass through the origin? Again, not necessary, correct? Because that depends on B, right? That depends on B, which,
The constant.
yeah, which is, I mean, it's not a constant. It's not a constant. It will change as we change the P, but I mean, it
Say
was
a fine.
yeah, it was constant in the context of this W. Okay, the constant of this one, this is a constant. Okay, other than the dot product, the remaining things we consider it as some P. Okay, now it need not pass through the origin again. Okay, yeah. So Laplace. Let's look at that also. So what will be the value of P01? So label 0, feature 1. Okay, first feature label 0. So this one we know. Okay, now the question is a binary classification with 0, 1. Now the labels are 0, 1, of course. Now the data points of n belong to 0, 1 power 4. Now the first feature, values for all the n examples are 1. So if for all the n examples, if the features value is 1, then what does it mean? If for all the examples, what the question is asking is, see what the question is asking is, P of 0, 1, which is what? Fraction of, this is number of 0 labels. In the numerator, what you will have? Number of 0 labels and feature 1 being equal to 1, correct? One label to be 0, but the feature to be 1, divided by this, right? Now let's say number of labels is not given. So number of labels, let's make it as n0. Now if all the data points have feature value to be 1, then definitely this is also going to be equal to n0, right? So n0 by n0, this will be equal to 1. Okay. Alright, so this will be 1. Okay. Now what will be the prediction for this? Now what is the prediction for this? See, the issue which we saw before was, if all the label values are zeros, if for some particular feature, if all the values are zeros, then we saw that the prediction turns out to be 0, right? If all things are zeros, then these two will become 0, right? Now if all are 1, then these two will become 0 now. If all are 1, then these two will become 0. Still overall everything is going to become 0, right? So on left hand side of the inequality you'll have 0, on right hand side also you'll have 0, which means you cannot predict. Alright. So if all the sides are 0, both are going to be 0, so you can't predict. Okay. It'll be difficult for you to predict. Next one, if there's any doubt you ask, okay? Is there any doubt? Fine, right? Okay. Now, consider an example of spam classification. Now, binary features again. Now, a word never appears in the training but appears in the test. What is the prediction for the email? Okay. So, again, I mean, this is the issue discussed there. So, some feature does not have any word in the training but has that word in test. What is the prediction? So probabilities for both spam and non-spam will be 0, correct? That's what we saw. The product overall, everything is going to be multiplied and you will get 0, right? Now you see, so what you should also know is, if all the emails don't have a word, don't have a particular word, then there's an issue. At the same time, if all the emails have a particular word, okay, particular word, but test data point does not have, okay, but the test data point does not have the word, okay. All the emails have a particular word, but test data point does not have. This is again an issue, correct? This is once again an issue, right? So in this case, what will you do? So if this is the case, what will you do? You add 0, 0, 0, 0 for all the things, with label being 0 and label being 1. Okay. So with label as 0, you add one data point, 0, 0, 0. With label as 1, you add another data point. Okay, so this will take care of this issue. Okay. Now this will very rarely happen, right? So maybe thank you or all those formal emails, they'll have thank you. So maybe thank you will have 1111 for all the data, all the emails. So maybe you can add 1 with 0, right? So if this is the case, then you will solve it with this. Okay. Fine. Now, if a certain feature takes a single value for all the training data points, and the prediction for a test takes different value for that feature, then the prediction will be indeterminate, as the probability will become 0. Now, what is the possibility to fix? Okay, that's what I discussed, right? So if all the words are present, you will add zeros. If that word is present in all emails, you add 0. If that word is not present, you add 1. Okay. Now you randomly assign a label to test point. So will you do that? You have a test data point. Will you randomly assign a label? If you do randomly, then let's say you do randomly with 50.5. For 50% of test data points, you will label it 1, and for 50% you are labeling 0. So definitely you're going to get a huge error. So this you should not do. But what you can do is add 2 dummy points with all features as ones in the training dataset. One corresponds to label 0, another corresponds to label 1. Now, what you should also do is add 2 dummy points with features being zeros. Now, with all features being zeros, that is also one more, right? In the training dataset, okay? One corresponding to label 0 and label 1, okay? So this is also, this is something which we discussed, okay? Yeah. For last one, but you should know why first one is not correct, because you will get huge test error. Okay, you will generally get a huge test error. Which of the following statement is true or false? Is the following statement true or false? If P of YA is equal to 0 for 0, then P of, okay, we'll have to write this carefully. What it is saying is P0 I is equal to 0. Okay. Now, does this imply P1? Does this imply P1 I to be equal to 1? That's the question, right? Is this the implication? Think and say. Is this the implication? The label is 0. If the label is 0, and if, see, what it is saying is, if we go back to this part, now for this one, it is saying that let's look at first feature. It's saying that the probability of heads is 0 here. Does that mean that the probability of heads is 1 here?
No, sir, independent.
No, right? Even within itself, there is no dependency. So this is definitely not going to have any impact on this, right? But what will have an impact is whether it is a spam or not. Okay, whether it's a spam or not will only decide whether lottery will be there with high probability or less probability. Okay, so there's no dependency on these two. But one thing which you should remember is this, there's no dependency, but P0i being equal to 0 will have an impact on yeah, of course it will have an impact on P0 1 minus P0i. Okay, so in that coin itself you will have an impact. Okay, in that coin itself you will have an impact for the other prediction, but outside the coin you will not have an impact. Okay, so for week 8 you try to visualize the diagram, and so that is the best way to solve. Okay, for week 8. See, while after looking at this coin and these two coins, you clearly understood that it's false, right? Okay. Yeah. Is this fine? Okay. Here, I think maybe we have not solved 8.3 and 8.2, but so that one you can try and we can maybe solve it later on. Okay. Clear. If there is any doubt, you can ask. Otherwise, we can leave. Is there any doubt? Okay. If not, we can leave. Okay. So thank you so much. All right. Yeah.
Thank you, sir.
Yeah. Thank you so much. So I think, yeah.